Hi, my name is Patrick Grady, and I'm presenting on a recent work, ContactOpt. When people interact with their environment, they typically use their hands to manipulate objects. Thus, it's critical for a computer to be able to track the hand and object together. Prior works have attempted to address this problem of hand-object pose estimation. This task is made difficult due to significant occlusion between the two shapes and the high relative pose accuracy required. This example demonstrates how difficult the task is. On the top is a ground truth sequence over time from the HO3D dataset, and on bottom are the results from a recent RGB pose estimator. There are large errors in the pose and inferred contact, making downstream tasks in simulation or virtual reality difficult. There are both large gaps and interpenetrations between the hand and object. When zooming into ground truth annotations from the dataset, these errors are still present. Even though high-quality sensors are used for annotation, clear gaps are visible between the fingers and the object. Due to the sensitivity of physical contact to very small changes in pose, this is not realistic, and the object would simply drop out of the hand. Achieving millimeter-level accuracy is required for physically correct and visually satisfying results. We argue that reasoning about the contact itself is an effective way to address these problems. Contact fundamentally describes the interface between two shapes, and it can be used to easily resolve these types of pose errors. Additionally, the contact can be used to inform pose estimation. For example, from only the contact map on this hammer, it is possible to estimate how it was grasped with reasonable accuracy. We introduced ContactOpt, which reasons about hands and objects together through contact. Our approach has 3 steps. First, we use an off-the-shelf image-based pose estimator to generate an initial, inaccurate pose. Next, we use a neural network to infer regions of target contact. Finally, we use an optimization to adjust the pose of the hand to enforce this target contact. Let's dive into how this works, starting with the contact inference network. We use a point-net-based architecture network to infer a target contact value for each vertex on the hand and object. Since the network uses geometric space as input, we find that it transfers well between datasets. In order to train the network, we use the recently released contact pose dataset. This dataset uses a thermal camera to capture the heat imprint left on an object after a grasp. We perturb the poses from this dataset while keeping the contact the same in order to generate training data. After contact inference, the optimization loop adjusts the pose of the hand to achieve this target contact. We develop a method to estimate the contact maps based on the current hand and object mesh. We use a distance-based method, where nearby hand and object vertices are marked as in contact. This function is differentiable. We implement this differentiable optimization using PyTorch. The loss function minimizes the difference between the target contact and the current contact. The loss function considers both hand and object contact maps. A penetration loss is also used to discourage heavy intersection between the shapes. We visualize the change in pose of the hand as the optimization progresses. Next, we show some of the results of this method. We perform an evaluation where we use ContactOpt to refine the poses generated by a baseline RGB pose estimator. We use the HO3D dataset for evaluation. The initial poses have significant error. The contact inference network first infers the target contact maps. Next, the pose of the hand is optimized to achieve this target contact. In addition to being more physically plausible, the refined hands are also closer to the ground truth poses. When hand contact is averaged over the entire dataset, we find that before applying our method, average contact is diffuse due to the inconsistent alignment between the hand and the object. However, after applying ContactOpt, a normal grasping pattern appears. We show that our approach is able to increase the accuracy of the pose estimator and reduce the kinematic error by more than 15%. Additionally, we performed a user study asking participants to compare the poses before and after ContactOpt. We find that they prefer the refined poses more than 85% of the time, showing that the refined poses are much more visually satisfying. Thank you. Please see our website and paper for further details.